In the deepest infrared observations of Venus, scientists have detected ancient traces of atmospheric escape, hinting at a dramatic past. These spectral signatures, unlike anything seen on Earth, reveal that our planetary neighbor underwent a catastrophic transformation. What could have stripped a world so similar to our own of its precious water, leaving behind an unimaginable wasteland? For decades, scientists have called Venus Earth's twin due to its striking similarities in size and mass. NASA's Magellan mission, launched in 1989, provided detailed radar maps of Venus's surface, revealing vast plains and volcanic features. However, beneath its thick clouds, Venus hides a secret, compelling evidence that it once harbored significant amounts of water. Today, Venus is an inferno boasting a scorching surface temperature of 460 degrees Celsius, hot enough to melt lead. Its atmosphere is 92 times denser than Earth's, composed primarily of carbon dioxide, with surface pressures equivalent to being 900 meters deep in Earth's oceans. This crushing toxic environment stands in stark contrast to Earth's life-sustaining conditions. This extreme state is a classic example of a runaway greenhouse effect, where positive feedback loops intensify warming. Unlike Earth, Venus's proximity to the Sun and its atmospheric composition created an irreversible process. Water vapor acted as a powerful greenhouse gas, trapping more heat and causing more water to evaporate, accelerating the planet's transformation. But how could a world so seemingly similar to Earth undergo such a devastating climate shift? We understand the general mechanisms, yet the precise sequence of events remains a complex puzzle for planetary scientists. Unraveling Venus's past could hold crucial lessons for understanding habitability elsewhere in the cosmos, or even for our own future. Early Venus, billions of years ago, might have been far more hospitable, potentially featuring vast liquid water oceans that could have lasted for hundreds of millions of years. Climate models suggest that with a thin atmosphere, conditions would have been temperate, making it a viable candidate for early life. This early period paints a starkly different picture of the planet. Venus initially resided within the inner edge of the Sun's habitable zone, sometimes called the Goldilocks zone, where liquid water can exist. However, as the young Sun gradually brightened, its increased radiation pushed Venus beyond this delicate boundary. This subtle shift was enough to trigger a devastating cascade of environmental changes on its surface. The faint young Sun paradox posits that the early Sun was about 30% less luminous than today, yet Earth had liquid water. For Venus, this meant a marginally cooler start, potentially allowing its initial oceans to form and persist. But even this initial advantage was not enough to prevent its ultimate fate as solar luminosity increased. As the Sun evolved and grew hotter, the amount of solar radiation reaching Venus steadily increased over eons. This gradual warming became the initial trigger for its atmospheric and oceanic demise. The planet began absorbing more energy, initiating a slow but relentless evaporation of its surface water. Water vapor itself is a potent greenhouse gas, far more effective than carbon dioxide at trapping heat in the atmosphere. As Venus's surface oceans began to evaporate due to solar warming, more water vapor entered the atmosphere. This created a positive feedback loop, trapping even more heat and accelerating further evaporation, pushing Venus towards a tipping point. The rise in temperatures caused by this initial warming led to more and more water evaporating from the surface of Venus, creating dense, superheated clouds. These clouds then trapped even more heat, forming an unstoppable cycle. This process, known as the moist greenhouse effect, was a crucial precursor to the full runaway scenario. Data from the European Space Agency's Venus Express mission, which orbited Venus from 2006 to 2014, revealed vital clues about atmospheric escape. It detected hydrogen and oxygen ions being continuously stripped away from Venus's upper atmosphere by the solar wind. This confirmed that the planet is still losing remnants of its water today. Crucially, as water vapor accumulated in the upper atmosphere, Intense ultraviolet radiation from the sun split the water molecules into their constituent hydrogen and oxygen atoms. The lighter hydrogen atoms with Venus's weak gravity easily escaped into space. This process was the primary mechanism for permanently losing Venus's vast oceans. While hydrogen escaped readily, the fate of the freed oxygen atoms is less clear, representing a critical mystery in Venus's story. Some oxygen may have been swept away by the solar wind, while a significant portion likely reacted with surface rocks, forming oxides and effectively rusting the planet. This geochemical interaction permanently locked away atmospheric oxygen. Unlike Earth, Venus lacks a global magnetic field, leaving its atmosphere vulnerable to the relentless onslaught of the solar wind. This absence meant there was no protective magnetosphere to deflect high-energy particles. Consequently, the solar wind could directly interact with the upper atmosphere, accelerating the stripping of atmospheric gases, including water's components. The surface of Venus shows evidence of widespread volcanic resurfacing, which appears to have occurred globally between 300 to 700 million years ago. Data from the Magellan mission suggests massive outpourings of lava covered most of the planet. This colossal geological event would have had profound impacts on its climate, potentially triggering further atmospheric changes. These immense volcanic eruptions would have spewed vast quantities of carbon dioxide and other greenhouse gases directly into Venus's atmosphere. This sudden infusion of gases would have drastically intensified the existing greenhouse effect. The planet's climate could have tipped into its current extreme state during or after these events. Unlike Earth, Venus lacks active plate tectonics, which is critical for regulating Earth's climate through the carbon silicate cycle. On Earth, weathering of rocks sequesters carbon dioxide, drawing it out of the atmosphere. Venus's stagnant tectonics meant no such natural mechanism existed to remove CO2, allowing it to accumulate unchecked. The immense amount of carbon dioxide in Venus's atmosphere, making up 96.5% of its composition, is the ultimate heat trap. This dense blanket prevents any heat from radiating back into space, maintaining the extreme surface temperatures. This atmospheric composition is a direct legacy of the runaway greenhouse effect and volcanic outgassing. Earth's carbon cycle is a delicate balance, where oceans absorb CO2 and plate tectonics recycle it into the crust, preventing runaway warming. Venus, without these crucial mechanisms, demonstrates what happens when that balance is broken. Its atmosphere holds hundreds of thousands of times more carbon than Earth's. Today, missions like Japan's Akatsuki orbiter continue to study Venus's atmospheric dynamics, including its super-rotating clouds and complex wind patterns. These observations provide vital data on how heat is transported and trapped within its thick atmosphere. Understanding these processes helps refine models of Venus's past and future. Future missions like NASA's Veritas and DeVinci Plus are poised to provide unprecedented insights into Venus's history. Veritas will map its surface with higher resolution, searching for evidence of past oceans and volcanism. DeVinci Plus will plunge into the atmosphere, directly measuring noble gases and isotopes to reconstruct its atmospheric evolution and water loss. Studying Venus offers a chilling warning for exoplanets discovered orbiting within the habitable zones of other stars. Many exoplanets might appear to be Earth-like from afar, yet could be entirely Venus-like beneath their clouds. Venus teaches us that being in the habitable zone isn't enough. Atmospheric dynamics are equally critical for long-term habitability. Despite its hostile surface, some theories suggest that the upper cloud layers of Venus at altitudes of 50-60 kilometers are temperate and host conditions potentially suitable for certain extremophile microorganisms. This increasing possibility has led to a renewed search for biosignatures, such as phosphine within the Venusian atmosphere. Another enduring mystery is Venus's incredibly slow retrograde rotation, where it spins backward relative to most other planets. A single Venusian day lasts longer than its year. Scientists believe a massive ancient impact or tidal forces may have caused this, and it likely influenced the planet's atmospheric circulation and overall climate evolution in profound ways. If you found Venus's dramatic transformation as fascinating as we did, hit that like button and subscribe for more cosmic mysteries. What do you think is the biggest lesson Venus holds for Earth? Let us know in the comments below.